Hello everyone, welcome back. Okay, so let's try this out, and as you can see there are no numbers for this problem. So when we do this problem, it's going to be completely in terms of variables, which is terrifying. I hate doing this, but at the same time it's a skill you need to have to, at least be able to pull out every once in a while. So what we're going to do, well, we're going to use the double integration method to find the equation of the elastic curve for segment AB of this beam. Only AB, that's all we care about. And we're going to find the deflection that's midway between the two supports, the slope at A and the slope at B. And we're assuming that the modular elasticity and moment inertia are constant and we don't need to calculate them. So that's enough for now. Let's jump right into it and we'll go from there. Okay, so first, a beam free body diagram. Now, we've done these kinds of problems a lot so far, so I'm not going to spend a lot of time telling you how to calculate those reaction forces. You've done it, just be very careful. You take the sum of the forces in the y direction, you take the sum of the moments about a particular point, you keep everything in terms of variables, and you solve. And you think to yourself, does this make sense? Well, AY is saying it's actually going to be pulling down, and BY is pushing up, which does make sense, because if we're going to keep it balanced, we're going to have one force going up in the middle and two forces going down on either side. Whoop. Okay, so now let's calculate the equation of our moment. What we're going to do right here is we're going to cut our beam, just like that. And now with that, we're going to make an equation for the moment of that beam, where x is measured from the left, going to the right. And so what we get then is we're taking some of the moments around this cut right here. We have, well, there's this equation of the moment as a function of x, because we don't know what x is currently. And that's going to be, adding to that is we're going to have this force P over 2, which is pulling down, times x, causing a moment. So what do we get? We get our moment equation is going to be simply equal to negative px over 2. That's it. That's our moment equation. That's what we're going to be integrating. And what you can see right here is that's a very simple integral. A very simple integral. So let's now do the integration of that moment equation. So first off, we set it up and say, okay, well, EI times the second derivative of our deflection is equal to our moment equation, which is equal to negative px over 2. We integrate once, and there's only an x there, so it's with respect to x. And so now we have the equation of our slope, and we have one constant of integration. We integrate a second time, and now we have an equation for our deflection and two constants of integration. So two constants of integration, hopefully we have 2 points where we know something about our beam, and we do, because we know at either support, the deflection is 0. So at either support, the deflection is 0. Because that makes sense. With how these forces are applied, and we have that support right here, we have a support right here, we have the force going down right here. Well, it's going to have to, bend upward, then come down like this. Something along those lines. But at both points, right here and right here, it has to be 0. The deflection has to be 0. So we use that. We plug it in. And what we see then is that, okay, if at x the deflection has to be 0, then, well, that's 0, that's 0, that's 0, and therefore, yeah, C2 is going to be 0 too. That's a fairly common situation where one of them goes to 0, so don't be freaked out if you see that. And then for our second one, at L, x is equal to L, deflection is 0. We plug that in there, and nothing disappears in this case. And what we get is that C1 is going to be equal to PL squared over 12. So therefore, my elastic curve equation is the following. Be very, very careful here. What you should see is that there's a force right here for both of these. That's good. There's also, this is x cubed, and this is x times L squared. That is length cubed in both cases. You want to see that length cubed in both cases, okay? If you don't have that, if every term doesn't have the same units, something's gone wrong. But we do that, and we're golden. So now we're going to use these constants that we've calculated, this one especially, to go back to our slope equation and say, okay, what's the slope at A and the slope at B? Oh, forgot about the deflection though. So this equation, we plug in L over 2 right here, and we simplify some, and we get, okay, the deflection at midspan would be PL cubed over 32 times EI. It's one of those nice things. Once you've done these problems a few times, you'll begin to see, like, okay, I have these equations. Maybe if I get lucky, one of the homework problems will have the same kind of setup with numbers. Maybe. Maybe not. Either way, you're learning how to solve them. Okay, now for the slope, we use our slope equation. We plug in the values for x. And we do it again, but now the values for x is not 0, but L. And we solve, and we can get our slope at both points. So, that is it for this problem. Thank you very much for listening. Hopefully you're beginning to get a little bit of an idea of how you would solve this. And I will see you all next time. Have a good day. Bye-bye.